Hi there, this is Mr. Sutton welcoming you to an intro to vectors. In this one, we'll perform basic graphical operations with vectors, and we'll figure out the new speed and direction for a hot air balloon under the influence of a gust of wind. For our warm-up, what is the difference between speed and velocity? Got it figured out? So this is really asking about the difference between a scalar and a vector quantity. A scalar quantity, like speed, has magnitude only. We're not talking about any kind of direction. Whereas a vector quantity, like velocity, has both magnitude and direction. We want to know what direction we're going. Now vectors can be represented a few ways. One way is with lines that have a tail and a head. So here is one possible vector. We've got a head here with the arrow, and the tail is the part that doesn't have the arrow. Let's do some real-life applications of vectors now. For this first one, they want us to sketch an arrow representing a ship's southwest trip, W, that's the name of the vector, of 200 miles an hour. So these aren't actually as bad as they look. You just have to pick a size, any size, and then get the direction right. So any size will do as long as it's going southwest. That would be down and to the left. And we'll stick a 200 miles on there to label this. Now, what if they want us to sketch 3W and tell what the trip is that it represents? So if you're multiplying a constant times a vector, what you're actually doing is making the vector that many times as long, whatever that k value is. So our arrow is going to have to be 3 times as long, like so, and then that would be a trip of 600 miles. The actual quantity itself, the distance, gets multiplied by 6. Next problem, sketch negative w and tell what it represents. So if you're doing a negative vector, you're just switching directions. You're just adding 180 to the angle, or basically just switching the tail with the head. So this time the vector is going to go northeast. This would be 200 miles northeast. Our next problem is going to have a little bit of a backstory. Let's say that a hot air balloon is flying in a direction with a velocity directed by the arrow labeled u below. So here's our hot air balloon. There's the vector representing its direction, and its velocity, and its speed. Now let's say that a gust of wind hits the balloon with the direction and the force shown by the arrow v. So here's our gust of wind, here's our v vector. What will the new heading of the balloon be? What we're looking for here is something called the resultant. This is the result from adding two vectors. So how would we add these together? So how do we add two vectors like u and v together? It's a two-step process. First step, we have to redraw one of the vectors at the tip of the other. It doesn't matter which one, because we're adding these. We can do this in any order, but I'm going to redraw v at the tip of u. When you do this, you should probably count squares to get an exact unreduced slope of your redrawn vector. For example, v is originally going left 3 and down 3. So the redrawn version of v should also go left 3 and down 3. And it has to be unreduced. I know this is really a slope of basically 1, but we don't want to reduce it because we want a vector that has the same size. So left 3, down 3 for v. Here we go. Next step, we're going to draw an arrow from the beginning of the first vector, that would be this tail of u right here, to the tip of the last vector, the head of the last vector. That would be the head of v. So from here to here, and the arrowhead's got to go in the direction that that last arrowhead is going. And there's our vector. And, just as importantly, that is the direction that our hot air balloon is now going to go. Based on what you know about vectors so far, see if you can perform this next addition here, or subtraction. All right, so first off, let's figure out what direction v is going. Again, that was left 3 and down 3. So before I draw anything, I want to come up with a way of expressing negative v. That's going to be the exact opposite direction. So instead of going left 3 and down 3, negative v goes right 3 and up 3. So I'm going to go to the tip of u again, because that was my first vector here, and then I'm just going to go in this direction. Right 3 is this way, up 3, and there we are. Now I'm going to draw that resultant arrow, beginning of u to the end of negative v, and this gives us our resulting vector. We'll do one more of these. This time do u plus 2v. All right, let's see how it went for you. So originally, again, v is going left 3, down 3. We're using the same v every time. And notice that it doesn't really matter where I put the v on here. It's all about the direction and the length, not the location. So if we start going this direction, 2v would just be twice as far in both directions. So left 6 and down 6. So putting it at the tip of u, here's left 3, left 6, and here is down 6. So we should be going there. And resultant, draw that from here to here. Make sure the head's going the right direction, and we're good. For our wrap-up, we'll attempt to answer the question, how many vectors can we use at once? So we want to sketch u plus v minus 3w. See how far you can get doing this one on your own. All right, let's see if you at least got a u plus v here. So u, just for the heck of it, we'll write out what it is. We're going left 4, up 1. And then for v, left 3, down 3. So that's what we have to redraw at the tip of u, because it's u plus v to start with. So we're going left 3, down 3, like so. But we're not done. From this, we now have to subtract 3w. w normally goes left 2 and up 1. But we're doing negative 3w, so I'm going to multiply each of these by a negative 3. This will now be right 6 and down 3. So we're going from here, right 6, that's over here, down 3 is here. So that's where our next vector is. And now the resultant, that's going to be from the beginning of this whole mess to the end, like so. So hopefully this example makes it apparent that we can actually use any number of vectors at a time if we want. Imagine having 12 or 20 or 100 different competing forces and trying to figure out what the result of that huge mess was. This is one way to do it. Until next time, this is Mr. Sutton signing off.